Okay, good. Okay, good. So let's start the class. So first of all, well, okay, my name is Giovanni Volpe and I will be the examiner of this course. Most of the other class, most of the time you will not see me in the next classes. You will see I could because it's going, get up. Show yourself. So it will I will be in class most of the time, but it will give the classes and I will be in charge of managing the homeworks. But I will give this class, which is an introductory class, plus a presentation of how the whole course is structured. Okay, so the first hour we will introduce the topic. The second hour we will see a bit, in detail how the course is structured, how you get your points, how you manage to get your grade. Okay. So before that, the class, as you know, probably Chalmers would like to have most of the classes in person, which I'm fine with. So this class is optimized for in-class attendance. This, but we are going to record it and share it on Zoom, but we don't guarantee the quality of the Zoom. In the sense, it might be bad, the sound might be bad, you might not be able to hear it. You will be able to watch it later on YouTube. We will put it up, but maybe the sound doesn't work. I'm just saying here now, from now on, it's just an extra thing we give. If it doesn't work, well, we are sorry, but it's not, the purpose is not to optimize it for Zoom and recording. You know, we have to choose. We cannot do both at the same time, okay? And Chalmers explicitly asked us to do it possibly in person. Same thing for the homework. We will have double option. You can, the homework you can choose. We will see that in the second hour, you can choose if to correct them in person or via Zoom or Gather. We'll see that. Okay. Any questions about this? Any doubts? Okay, good. So let's go to the first hour of this class, which will be essentially a presentation of the topic. And as you know, this class is simulation of complex systems. So let's start with some questions, and I will, since we are in class now, we can do it very effectively in an interactive mode. So I will ask a question and I do expect you to answer. So what characterizes complex systems? Yeah. Okay, so complex systems should have many parts. What else?
Chaos.
Okay, there might be chaos. What else can you? What else do you associate with complex systems? So there are dynamics. What else? Okay, interactions. Not easily mathematically defined, which practically means that you cannot just write easily a formula and find out what are the properties of the system, right? Okay, so this is all the idea. So there are plenty of this is just a cloud, a word cloud with the things that usually people come up with when you ask them what are complex systems, what defines complex systems. You see that you said several things of, several of the words that you came up with are there. There are other words that you didn't come up with, but you know, it's a random process. Also, the one what you come up with. So you see that there are really plenty of characteristics. Okay, so if you really want to define them, if you want to write a definition of complex system, what would you say?
A system in which you can have full knowledge of all individual parts of the system.
Okay, that's a good point. So you have a system where there are multiple parts and the whole system behaves in a way that is not just the sum of the parts. Usually people say that, right? What else? Any other ideas? How would you define? If you had to write down a definition of complex systems, what would you say? So if you want to write a definition of complex system, we can say that, as you said, essentially, it's a system constituted by many parts interacting, many interacting parts that display emergent behavior. Okay, is this clear? So let's see which ones are the keywords here. So one keyword is the fact that you have many interacting parts. So typically in a complex system, you will not have something where you have a single element or a single object, but you will have many parts. And this part must be interacting with each other. So there is some interactions going on between the parts. And they display emergent behavior, which is essentially what you said before. What does it mean, emergent behavior? It means that the ensemble behaves in a way that you cannot just, basically the whole is more than the sum of the parts. This practically means that you cannot easily imagine how the whole, a system as a whole will behave just by knowing the properties of the behaviors of its components. Is this clear? Can you give me an example of such a system? The brain, in what sense? Okay, so if you think of the neurons, of course, we know pretty well how neurons work, but obviously it's still an open question how you go from single neurons to complex thoughts. If you think of awareness, that is definitely not explained.
Any real life behavior such as maybe.
Okay, in what sense? Can you give me? Yeah.
In the economy of country, there are a lot of interacting parts. We just can't predict the accurate future.
Yes. So that's a very good point. Economics, even if you know each agent, how they behave, you have plenty of emergent behaviors. You don't really know what happens. What else? Sorry? Firefly? Okay. Okay, so you mean synchronization in fireflies, the fact that the multiple fireflies can get to synchronize their behavior and how that happens. Of course, synchronization phenomena are an example of emerging phenomena because they happen. I mean, the example of the firefly, but also the brain for that matter. The interesting part is that you get synchronization without a global timestamp. There is no one giving the signal to the fireflies how to synchronize. Okay. I don't know, in a concert would be like having a concert without a director and instrument playing together well, but without anyone imposing the order to the concert. Okay, good. So those are some examples. And we have already done most of them, but let's go to different topics. So first of all, we can think of physical systems. So you have said several of these, but so this is just to give you a more extensive overview of examples of complex systems. So in physics, you can think of these systems. So you can go from condensed matter physics. Okay. So can you think of examples in condensed matter physics? So what is condensed matter physics is clear? Okay, essentially, the physics that touches you more directly. Hard condensed matter will be everything that you do with your computer, your cell phones, they work because of hard condensed matter. Soft condensed matter is biological materials, for example. Anyway, I just gave you, any example in condensed matter physics, as soon as you move away from the constituent element, it becomes complex systems in reality. So you get your phenomena like criticality. You can think of hundreds of hydrodynamic systems are very complex to understand. This is still one of well, the reason is because you have a transition towards a turbulent behavior where you cannot just solve the question. You know that in a turbulent regime, it's still an open question of whether there are or there are not a unique solution in certain regimes and so on. So that's important. Or if there is a solution and if it's unique, it's an open question. And you might know that there are some prices, like $1 million price if you can solve that. spending from I don't know how many years. Pattern forming systems like the fireflies that you were mentioning, computing, obviously, biophysical system of any sort, molecular self-assembly, all of these are problems in which you can see the complexity emerging from the multiple constituents. Then, if you go to biological systems, obviously, you can see that these are all complex systems. So food webs, ecosystems, biological evolution, these are all examples of complex systems. And I guess I don't really need to motivate that. It's pretty obvious, right? You see that. And if you don't see that, try to think. I mean, it's very nice. Food webs, for example, something that now many, if you, I don't know, if you read the New York Times, I think this week, there was a nice podcast. Well, not a podcast, it's more, they read an article, the Sunday Read in the New York Times, which is about what happened when in the US, basically in the US in the 70s, they introduced a law that protects marine mammals. Means you cannot kill seals. Okay? Then what happened after that is that in the West Coast, I'm sorry, in the East Coast, the number of seals went up, which is good, obviously. But then this means that the apex predators, so the sharks, came back. And now, obviously, they are complaining that they cannot swim as safely as before because there are sharks. Of course, it's their medium, so they should be there. But, you know, there are unintended consequences and good consequences most of the time because, you know, the shark keep the humans out of the water. But the same way that wolves have a very good effect on ecosystems because they might keep deer from eating small trees. So you can get forests to regenerate themselves, thanks to the introduction of an apex predator, which was seen in the Yellowstone Park a few decades ago. Okay, so it's really a very complex system, and it's pretty obvious why. Human societies, again, it's pretty obvious, but you see why? Can you give me examples in human society when you see complex systems and emergent behaviors? Any example that some emergent behavior, so something that is not intuitive that happens when in a human society, when
there's a saw a video of the restoration of some streets in the US a few years ago, where they made it more livable and they cut off cars from going there, and you know, they made it so they can make events during the weekend, something like that, and then they started here. The city is starting to develop like a little cafe culture thing.
Yeah, so that's one example where you introduce something, some law for some new properties in a system, and then you find some emergent behaviors. One nice example is actually from Stockholm, because well, I don't know if you know, but I don't know how many years ago, like 30 years ago, Stockholm was extremely congested in terms of traffic, right? You know that, or you know that now? So Stockholm had very big problems with traffic, essentially because there were too many cars and going around, and obviously what is that, you know Stockholm, I guess. It's your capital, so you should have an idea. You know that there are several islands connected by bridges. Okay, that's what you need to know. So obviously, what is the most simple solution if you have a lot of congestion, a lot of traffic in a city? What is the first thing you would think of? Add more streets, add more bridges, and this will help cars going around and therefore reduce congestion and traffic. This is clear, no? That's the most intuitive thing. Well, the point is this, they got IBM to research the problem before implementing any new choice. The idea was to build a new bridge. And the question, I think, was to where to build the bridge. The conclusion from IBM, which, I mean, you know, IBM, essentially what they did was to simulate the city and see what happens under different conditions. Okay, so the same kind of simulation that you will do in this course, by the way. And this was 20, 30 years ago, so probably the computer power they had is similar with what you have now, just to give you an idea. So anyway, what they concluded is that if you add more bridges, what will happen is that you will have more traffic because more people will go around the city by car. So therefore, what they suggested was to introduce the congestion charge. So you know the tax that you have to pay when you go to Stockholm or Gothenburg because you come by car? Well, that was introduced at that point, and that actually solved the problem because then you get less cars and people, and then this practically means has knock-on effects because then you have more streets that can be free for people to walk around. So people will choose walking more easily. You get more people to go by bike, you get more people to use public transportation because it's faster and more efficient, you know. So that was the solution, which is not totally intuitive. And the nice thing of this is that it was actually solved making a simulation of a complex system. You might not like the fact that you have the congestion card tax, but still it works well. And it's been copied in many other cities. And by the way, many other cities have approached the problem of traffic in a similar way. For example, by closing some streets to traffic. So the idea, if you close some streets, you might actually reduce traffic, which is not intuitive. Or if you make streets one way, because essentially you tune the traffic and you make the traffic more efficient. Okay. Many of you might know the fact that UPS some time ago studied the fact that if you turn always left is better than if you cross the incoming traffic in terms of fuel efficiency and time that it takes to go around. So. Okay, so this is an example, economical systems. Again, it's pretty obvious these are complex systems. Can you give me some concrete examples of your interest? Where you see complexity in
Stock market.
well, stock market for sure. And how you see that that's a complex system?
Hard to predict.
Hard to predict, and obviously people don't know what they're doing in the sense that and when I say that, I'm really saying economists don't know what they're doing, or they don't care about not knowing what they're doing, because, you know, all classical economic theory, which is still being used nowadays, most likely your pension funds are studied and optimized using classical economic theory, which relies on the idea of essentially the idea that things are Gaussian. The problem is that has been clearly shown that things are not Gaussian. And you say, who cares? Well, you should care, because this means that the deviation in average might not be finite. Which means that you think that you have a certain risk profile. Well, that's true if it's Gaussian, the system. If the system is non-Gaussian with infinite variation, then the risk profile doesn't mean almost anything. And if you want to know more about that, of course, you can read a very famous book by Taleb, which is called The Black Swan. Do you know that book? If you don't know it, have a look at it. If you know it, read it. It's a nice book, explains all these things. Anyway, complex systems, and very nice here because the complexity is really related with the non-Gaussianity of the system. So the fact the system goes beyond, well, okay, maybe a question that might not be too much related with complex system, but it's still interesting. Why people, yeah, what does it mean? Why people study, why economists like to study economic system with Gaussian-based theory? Because it's easy. I would say something a bit stronger, because you can calculate things with Gaussians. You have a lot of nice formulas. When you make the Fourier transform of a Gaussian, you get another Gaussian. When you sum two Gaussians, you get another Gaussian with the sum of the mean and the sum of the variances. I mean, it's beautiful to make calculations. You can calculate things, go very far. With non-Gaussian distribution, you cannot do any of that. So you are stuck mathematically. You cannot do much. What can you do if you have a non-Gaussian distribution in your system? What do you have to do? If you want to study a system that is non-Gaussian, if it's Gaussian, beautiful. You can make formulas. You can end up with a formula. You can come up with a Black-Scholes formula, which is the one that gets the Nobel Prize to the economists for the futures. You know that. Fine. If you are not Gaussian, what can you do? Simulate. Yeah. The only thing you can do is to simulate the system. And we'll see in a moment why simulation is not very much. I mean, until very recently, it has not been very much in vogue, let's say. Okay, other example, collective phenomena, obviously. You mentioned some collective phenomena before. What else can you think about? Can you tell me some examples of interesting collective phenomena that show complexity and
And colony.
Hmm?
And colony.
ant colony for sure? What else? And you will have a whole chapter about that in the course. There is a chapter titled Ant Colony. I think it's the last one more, right? Probably.
Yeah.
What else?
Crowd control.
Hmm?
Crowd control.
I understand.
Crowd control. Emergency.
Crowd control, yes, sure. Yes, also that's a very nice topic actually. How you control a crowd and why do you want to control a crowd, by the way? This is a very common topic for projects in this course, crowd control. Why do you want to control a crowd? In which cases do you want to control a crowd? In a queue for sure. If you go to the airport right now, you see that airlines became very, very, yeah, they got very crazy with the way in which they board people on planes because everyone, you know, they go by row, inverse row, whatever they. But for example, a very concrete problem is to get people to escape in case there is a fire. Then you want to ensure that people can escape in the most efficient way without dying because they get crashed by other people, which happen in many cases. There were big cases of that in famously in a concert in Germany. There was a big case like that in the Kasbah in Saudi Arabia, where many people got crushed. You know, when in the, what's the name?
Mecca.
In the Mecca, yeah. They have to go to Mecca, Muslim, once in a lifetime, I guess, and at least. And they go around the meteorite that fell. And in doing that, if you don't control the crowd, they crashed, and that happened once. So, you know, you really want to control the crowd. And there are ways to control the crowd, very simple ways. Again, if you go to Stockholm, have you ever been to the train station in Stockholm? Have you noticed how they control the crowd, in which side you should walk? Not very well, but if you go to the train station in Stockholm, you see that there are advertisements on the side of the wall, and they are filtered. So you only see them if you come from one side and not if you go in the opposite direction. This is a very subtle way. Well, it obviously goes the way you want people to see the advertisement because the advertiser pays for it. But you also control the flow because you tend to stay on the side of the corridor where you can see the advertisement because it's more natural. And there have been studies of these things. So it's not, again, lots of studies with simulations. Okay. And next step. So these are examples, definitely not an exhaustive list of examples. But what can we do to study complex systems? What methods can be used? Well, obviously simulations, and that's fine, but can you be more concrete than that? So examples? Okay, so you have plenty of methods to study complex systems. You don't have, in the simulation area, there are plenty of techniques. And here you see some examples. So you go from, well, networks, dynamical systems, which means stochastic differential equations, cellular automata, scaling behavior, game theory, information theory, complexity theory, agent-based model, Monte Carlo simulations, plenty. There are plenty of techniques. Do you know any of these already? Yeah.
Yeah, I studied game theory when I was in my training. I remember the problem we talked about with roads. It's true in game theory as well.
What was?
When you added more roads, you got more traffic.
Mm-hmm.
I remember that's not game theory.
Yeah, that's yeah. Yes, I mean, we will see game theory during the course. For the ones that don't know what it is, you will see it. But for the ones that know what it is, of course, traffic is a typical game theory problem. Why? What aspect of game theory can, I mean, how many of you know already the prisoner's dilemma? Can you raise your hands? Yeah. Okay, there is a good share. So, you know, it's very similar to traffic. You see that? If everyone took the optimal average road, then the traffic will be much better, everyone will be better off, but people trying to optimize their own way to go around the city. And that's why introducing more single one-way streets and closing some streets can optimize the flow of the traffic, because you prevent people to optimize too much their own path, which end up typically having everyone taking more time. So it's not good for them either. It's just that if everyone optimizes their own path, you end up having everyone late. But yeah, we'll see game theory. What else?
Dynamical systems.
Yeah, I'm sure the dynamical system is the one that you have mostly seen. Why? What are dynamical systems? System that change in time, and system, as you see there, that you can describe with a set of differential equations. So if you think about it, Newton's equation are dynamical systems. So I'm pretty sure that all of you have seen dynamical systems. Maybe you have not studied them in terms of dynamical systems. In the sense that maybe you have not studied their stability, Jacobian, Lyapunov exponents, I don't know. So maybe you have not studied that part, but for sure you have seen plenty of dynamical systems. Because anything you can describe with a differential equation, it's a dynamical system. Okay, so now, okay, before we go here, you can see here, these methods are not necessarily methods that require simulations. You see that, right? What we said about game theory or dynamical systems is really can be done with formulas, and it's done often with formulas. So the question that arises is, why do we want to make simulations?
Can you explain the scaling?
Which scaling?
Scaling and criticality.
Scaling and yes. So okay, scaling and criticality are a bit two different things. But scaling, okay, do you know what is a scaling argument? What is scaling? Yes, scaling. Okay, I give you an example. Scaling essentially studies how systems scale with size. Like, let me give you a concrete example. Give me a second. So imagine, for example, okay, think about mammals from, I don't know, from a dog up to an elephant. You see that if you measure the weight of this animal and the size of their legs, just the circumference of a leg, you see that an elephant is not just a zoomed out version of a dog, right? You see that? Why? Can you see that an elephant is not just a dog zoomed out or enlarged? What happens if you take a dog and you make it the size of an elephant? Well, which, by the way, is what, if you think about Dali, you know Dali, right? The impressive, the surrealist painter and other things. Well, one of these paintings is really making an elephant as an animal that has the size of an elephant, but the legs to scale of a dog. Well, that will not exist in reality. It's surrealist for a reason. And the reason is that it will break the legs. Okay, so this is scaling behavior. So if you want to scale the size of something, then you have to scale other things with a certain power law. Trivially, think of a sphere. If I increase the size of a sphere, the volume will increase with the cube of the radius, but the surface area will increase with the square of the radius, which practically means that the amount of skin around an animal doesn't scale like the weight of the animal. And same thing for the cross-section of the bones of an animal. And this puts serious, this puts some constraints on how big an animal can be and other things. Okay, so this is scaling behavior. Criticality, and if you're interested in scaling, there is a very nice book also here by Geoffrey West which is titled Scale. Do you know this book? If you don't know this book, read it. It's very nice stuff. So it's a very big book, but it's very nice to read. Scale by Geoffrey West, which is one of the main scientists that has been studied for the past 40 years, scaling behavior. Just to give you an example of a scaling behavior, which you can test yourself, the amount of steps that you make depends on the size of the city where you are. It's a very specific scale. So if you go to a larger city with a more population, you will do in average per day a different number of steps. You can test it by yourself. Go to a small bit. I mean, I guess when you go on vacation, you go to different sides of city, you will see that the bigger the city is. I checked it. When I'm in Gothenburg, my number of steps is less than when I'm in Stockholm. Not because I do it on purpose, just because. And when I go to a much smaller city, it gets smaller. So this is a scaling behavior. Just to give you another example, how many gas stations are there in a city? So if I have a city of 1 million people and I have 1,000 gas stations, and I give you a city of 2 million people, how many gas stations do you expect to find there? 1 million, 1,000 gas stations. 2 million, how many gas stations? Can you guess?
1,500.
What would be the most obvious guess?
2,000.
And obviously it's wrong, because otherwise we will not make such a big deal. Okay, it's less than 2,000. There is a scaling factor, which I don't remember. It's, I think, something like 0.87, which means that you increase the size of a city and the number of gas stations increases less than proportionally, which is the reason why if you go to larger system, you can have economy of scales at the end. Okay. And it's connected to fractal dimension and so on. Criticality is another thing where a system can naturally converge towards a certain state, simply because it's a critical state. It's like having a stable point, but in a system. Okay. And it's very interesting because you can have a system that have self-organized criticality, which means they tend to organize themselves close to a critical point. And the reason is because, well, the suspicion is that this is due to the fact that near a critical point, the system is much more sensitive to changes. So a small change in the environment receive a big response from the system. You understand that this is very convenient for biological systems in many cases. But this doesn't happen only with biological systems. It happens also, for example, with the earthquakes, because there is a self-organized criticality in the way in which the earthquakes are distributed, which, by the way, leads straight into a power law. That's why the two things are connected. Okay. Okay. More questions? Okay. So why simulations? So why do we want simulation? We can study most of these things without simulations. We can write formulas, nice formulas. Why do we want to use simulations instead? Yeah.
It's too complex or demanding to try to evaluate each formula. For example, the powered agents, the style, and it's easier to simulate.
Okay.
Maybe with formula, it's like deterministic, or we don't have that. You can see something in the simulation that you may not see in the formula.
Okay. So these are good answers, but I just want to move faster because I'm out of time almost. So these are good answers. We'll get back to this. I just want to give you an historical perspective on this. What does it mean? If we go back in time to the Greeks, what do we find? How was Greek science working? So if you were in a Greek class, what would you be studying? You will be studying geometry. Why? We will be probably on some, I don't know, for example, on some sand, drawing circles and squares and understanding the relationship between them. What is the most famous thing you know from Greek science?
The Pythagoras theorem.
Which is a theorem about geometry. I'm not going to say the period of it because I assume you know what it is. But what was the biggest problem in Greek science? Why people got killed in Greek science? Well, Archimedes, very famously, you know, he got killed. Why? You know who is Archimedes, I guess. Well, where was he from? Syracuse, right? So, and why? How did he get killed?
Maybe because they were irrational numbers.
No, that is why Pythagorean got killed. Archimedes got killed because you know, he participated very actively in the defense of Syracuse against the Romans, and basically what he was doing, the story goes that he was studying some geometry on the shore, on the sand, and a centurion, a Roman centurion came there and said, "Get up, what are you doing here? Go away." And he said, "No, no, I have to finish this theorem," and he killed it. It's nothing to do with the course, obviously. But more relevant, the fact that Pythagoreans killed people because of irrational numbers. Why did they kill people? What is an irrational number, just to be clear? Which irrational number are we speaking of? Any square root you like. Square root of 2 is the typical one that is mentioned, but also the 5 is an irrational number, which is very relevant for Pythagoreans. But anyway, square root of 2 is very important because practically it tells you that you cannot build the diagonal of a cube by items that you can use also to build the size of the cube or square. You understand the problem? If your word is based on geometry, this is a big deal. And it was a big deal. But this is geometry. And by the way, geometry kept on being the basis for science until when? It's not only the Greeks that care very much about geometry. Until when was geometry fundamental in science? Yeah.
Like the 16th, 17th century?
I would say even 18th century, 19th century. Because why? Mainly because of Euclid and the book of Euclid, in which he was systematizing everything based on 5 axioms, very famously. And okay, so that was seen as the pinnacle of science and human knowledge, and everything else should have been done like that. Okay, so all Middle Ages science and theology was really admiring Euclid and geometry. Things changed only when calculus came about, which was in the 16th century with whom? Who invented calculus? In Newton and when? Okay, exactly. Both of them at the same time, and they thought about who was inventing it. And that's, by the way, why you have 2 notations for calculus, because they were, you know, with the dot, with the t over the x over the t. They are the 2 notations that they were favored by Newton and Leibniz. Anyway, the point is that they came up with this in the 16th century, and it took 3 centuries before people accepted calculus as really science. So until the 19th century, people were still worried about geometrical facts that you don't care about. Give me an example of that. That's another story. Of course, non-negative numbers, but imaginary numbers was a big deal. And the reason why they are called imaginary numbers, that's a nice story in itself. Because, you know, complex number and imaginary numbers, when were they invented?
In 1700. From
Yes, but
when this cubic was off.
the problem, yes. So people knew about something like imaginary numbers very early on, even during the Greek time, but they imagined it was only a trick to calculate things. You know, when you have a cubic and you intersect with a straight line, you can have 1 intersection point or 3. To calculate when you have 3 intersection points, which are a geometrical fact, therefore existing and relevant, well, then you need an imaginary number to calculate these facts that exist in reality. So, you know, they were using them, they were not liking the fact that they had to use them. People started liking, understanding, and accepting complex number when they could interpret them geometrically. And that was with Cartesian. The Cartesian, basically, imaginary number, complex number are points in the plane. Essentially, x, y plane, like Cartesian coordinates, it's essentially complex numbers. When people understood that, they accepted them. So just to give you an idea how important is geometry in the thinking of until that age. Anyway, 19th century, people still were worrying about geometry a lot. One of the big problems was how to build with a ruler and to divide an angle into 7 parts. You cannot do that with a ruler, but they were trying to do that with a ruler because it's a geometrical issue, which is therefore very important. You don't care about that nowadays because you don't care about geometry, because you care about calculus. That's what you care about right now. So we are in a phase which started in the 19th century and lasts until now, in which people care a lot about calculus, about formulas, having nice formulas. That's why you study the harmonic oscillator, and you spend probably a lot of time studying the harmonic oscillator, but you don't study what happens if it's like an harmonic. That's why you study Gaussian probability theory, but not what happens when you have non-Gaussian distributions. Understand? The reason is because calculus was incredibly successful with with mechanics essentially, thanks to Newton. And I will say that now we are in a new phase, which started probably maybe 30, 40 years ago, in which we are going towards simulations. And you can see that because now people accept more and more the fact that you can do things with simulation, you can prove reality with simulations. One important thing that happened just a few years ago is that mathematicians started accepting demonstration made by computers. Until a few years ago, a mathematician would tell you, no, a demonstration of a theorem must be done by a human. So if a human writes an algorithm that tests all possibilities of a certain theorem and a computer verifies that they are all true, that's not a good demonstration. You see the problem? So the idea of doing this in mathematics has been accepted probably not by all mathematicians, but very, very recently only. So you see that now we are entering a new phase in which people accept simulation as a way to know reality. Okay? When did this happen, in your opinion? Yeah.
Fermat's last theorem
No, the Fermat last theorem was demonstrated by
hand.
Yes.
I thought they simulated. Okay.
No, that was what was demonstrated with by a computer was something group theory, where they had to basically check a huge amount, I don't know, many billions of groups of and check that all of them had certain properties. But Fermat theorem was, you cannot demonstrate Fermat theorem by simulation because you have infinite numbers.
The Shannon limit.
I mean, okay, so for the sake of time, I think the very early demonstration that maybe analytics calculation are not enough came with Poincaré, end of 19th century. You know why? The so-called three-body problem. You have heard of that. In classical mechanics, the problem is that you can predict perfectly how the moon rotates around the Earth as long as there is nothing else in the universe. As soon as there is something else, you cannot guarantee that your prediction is stable. And that's the reason why you cannot just launch a spaceship to Mars. You have to keep on correcting the trajectory because you have small corrections that might grow out of control. This is from Poincaré, end of 19th century. But then very much Lorentz in the 1960s came up with a real demonstration that simulation and numerical error matters. You know, the famous problem in which he demonstrated that predictions of weather might change a lot if you change the digit in the initial conditions. The reason why you cannot predict weather longer than a few days, because the system is intrinsically unstable. And there, you see, this is really what the early start of the idea that simulation might play a more and more important role. And of course, afterwards, the power of computer, with the increase of power of computers and so on, we came into the new era now that simulation are really deciding policy. Just to give you a very, very clear example that is occurring just these days, where you see simulation playing the role in policy and economics right now in Glasgow. What is happening in Glasgow right now?
Oh, Frankie,
Okay, what is that? Yes,
climate conference.
climate conference, but who decides, who informs all the decisions that are made about climate? the hard science comes from simulations. There is no analytical model of the planet of the Earth. Of course, there are formulas that are used in simulations, but then it's just large-scale simulations and study of their stability and reliability, which determines what are the inputs that should be used by policy and economics to make appropriate choices. So you really see that the power of simulation where it plays out at scale. Okay. Okay. And yeah, with that, we should have a break. And during the break, well, is there any question you can ask now? And during the break, if any of you would like to be course representative, let me know now. If not, I will just pick the ones that are chosen randomly by the, I don't know, someone send me an email with a list of names by that person. Okay, is there any question? Okay, so let's have a break until 11, and then we continue with the second hour. Stop the recording.